Thank you. My name is Tassos. I'm with RF Elements, and today we'll be going over our RF Elements Noise Rejection 101 webinar. So at RF Elements, we deliver fast, sustainable wireless, and we do this by offering antennas that give you ultimate noise rejection, specifically speaking about our symmetrical horn antennas. These horn antennas are very unique in that they have no side lobes and very precise radiation angles. When you couple that with our proprietary twist port mechanism, these twist port devices give you the ability to interface with many manufacturers' connectorized radios in small form factors and allow you to tap into our twist port ecosystem. And this gives you nearly zero loss because of the very tuned and deliberate connection interface. When you bring these two things together, that gives you the massive scalability that you need as a WISP today. The demand is clearly growing day after day, not only for the demand of the number of internet connections that are needed around the world, but also the amount of bandwidth that's delivered by each one of these connections. So the only way to really meet the massive scalability that's needed for growth in today's WISP industry, you need RF Elements antenna technology to get there. So if we look at the challenges today, the key challenge is spectrum, right? And it's not just a question of the amount of spectrum that's available for you to operate in, which varies, country by country, region by region, but it's also the amount of usable spectrum that's within that finite resource of available spectrum in your area. So using the proper antenna technology that allows you to be as spectrally efficient as possible is really important in today's WISP market. And really the problem with the spectrum that we have is really, boils down mainly to antenna radiation, right? So antennas, with side lobes are inherent with most legacy solutions that are deployed today. So if we look at our traditional patch array sectors, these antennas have inherent side lobes. It's something that's very hard to deviate from or get away from because it's part of the physics of how that antenna is manufactured, and therefore side lobes is a product of that technology that, in some cases, you might be able to influence it some, but you'd never really get rid of the side lobes. These legacy antenna technologies really do not allow for exact beam angles either, by not having appropriate radiation properties, right? So the beam angles out of patch array traditional sectors, they vary, not only from your chain, your vertical to horizontal polarization, but even the gain within those polarities also deviates. So it's not just a question of just the angle in which it propagates, being inconsistent, but it's also the gain or the distance that radiation pattern can go is really affected by this, again, poor old antenna technology. And the RF noise is really just a result of this old technology being deployed day after day in the field, and it's causing issues mainly for yourself, but also for others, for your competition. So it's not just issue on your particular tower, in that one location, but it could be your other towers within your coverage area, depending on how spread out your coverage area is, what tower density you have. Really, side lobes create problems all around. And again, it's really an old, poorly designed, outdated technology that's really not sustainable for growth. So we need to look beyond the old ways and look at some new ways and new antenna technologies to deal with the newer radio technologies that we have today. So basically antennas, with inconsistent beam angles and huge side lobes is the issue. And this is the solution for that is horn antenna. So if we'll look at some different types of antennas. So if we look at the omnidirectional antenna, for all intents and purposes, I mean, an omni is really one big side lobe, right? It's the epitome of transmitting everywhere when you don't always have to, and it's really hard to get away from, right? So if we look at a deployment, there's always areas of coverage where you have no customers. And again, this antenna radiation pattern basically is like having side lobes within those areas where your antenna can hear or send signal where you don't want it to go. So an omnidirectional antenna in today's networks is there's really no place for it, right? So it's one big side lobe. It causes nothing but issues, single point of failure. I mean, there's a ton of issues associated to using omnis, and really we should try and avoid that whenever we can. So if we look at a patch array sector, this is your traditional sector, we can see the highlighted areas. The highlighted areas are the side lobes. They're usually above and below the main lobe, but really off the back into the sides of a patch array sector. So if we look at it in 2 dimensions, we can see how, when we have it deployed by itself, it's able to receive and send noise. It receives through side lobes, and also by using traditional sectors that are much wider than the coverage area that you need, right? So these, again, give you the potential to receive noise from competing stations, from competitors, also receive or interact with your co-located antennas on your tower. So it really starts to create this issue of channel reuse becomes very difficult. Co-location and noise floors start to grow when you have side lobes and really high gain antenna. So patch array sector antenna really has a lot of issues with beams being too wide, too many side lobes, and therefore your network throughput can be greatly affected by that. The same can be said for parabolic dish antennas. If we look at it in 3 dimensions, again, you can see the highlighted areas are the side lobes. The side lobes are any secondary lobe outside the primary main lobe, right? So all these lobes send and receive signals to areas. So again, in the standard point-to-point, you're typically thinking of that main radiation beam angle as if that's the only part of the antenna that's actually working. And if we look at the side lobes, they really start creating issues. Again, when you're co-locating, if you have backhaul links that are shooting, through your tower that are not within the same azimuth of your main beam, these side lobes can pick that up, whether, again, it's one of your own backhauls from another tower coming across or a competing one. So again, side lobes interact. They're there. No matter how small they may look in your polar plots or your spec sheets, they're actually much larger than you think and cause huge issues for yourself and for your competition. So again, side lobes are really a huge no-no, right? Again, if it's your only antenna on there, you might say, well, it's an area of noise reception. But as we start building out our towers, as we start adding our second, our third, or maybe even 4th traditional patch array sector on the tower, we can see now where the areas of contention are, where these side lobes start interacting, where these really maybe much wider beam angles than are needed, how they start interacting with each other, and this just raises the noise floor, creates issues for, again, frequency reuse, and really makes it difficult for the radio to spend the time and focus mainly on delivering packets to your customer, which is the most important. But when it has to deal with noise, it really starts to drag down the overall tower performance. And it's really, again, it's a quite outdated antenna technology based on the really high demand that WISPs are finding themselves in delivering higher and higher throughput packages to more and more or more densely populated deployments. The same thing happens with backhauls. Again, we often think about that narrow 6, 7, maybe 8 degree wide main beam, and we think that the rest of the radiation pattern really is null and void, and it's not. If we see backhauls on our towers, we can see how those side lobes interact with the other backhauls on our tower, and even again with competitors' backhaul, whether they're co-located on your same tower, maybe 20 or 30 feet up or down the tower. Maybe it's on a grain leg where you have these big distances. Again, these side lobes are capable of interacting, hearing, and talking to each other, and really start causing issues and reducing your overall backhaul throughput, which is again a huge problem, because without your backhaul, you're not getting that bandwidth that you need to your tower sites to again deliver all this bandwidth that's required of your customers. So the solution are antennas with precise beam angles and no side lobes. If we start taking away those side lobes and we see how these antennas now don't interact, how these coverage areas really don't bleed over or interact with each other and overlap, we really start creating a system, and we really start having wireless networks and radios that are capable of performing much closer to the actual spec speed and throughputs that the manufacturers put on their box, right? It's quite often heard or spoken of how these radios are capable of delivering these speeds in theory, how they put these high speeds and high distances on the box, but yet people never see it. And they just chalk it up for noise and say, well, that's the solution. That's the world we live in right now, and there's nothing you can do about it. Well, there is something you can do about it. If you have the right antenna solution, antennas with precise beam angles and no side lobes, you'll start seeing your radios delivering the throughput that's promised from the radio manufacturers, and have yourself a much more stable WISP. So let's look at point-to-point antennas here. Let's see if we start replacing parabolic dishes with, let's say, our ultra horn, which is our point-to-point antenna technology. You can now see that your two co-located antennas are now dealing with a lot less noise from each other, and therefore the radios are more busy now delivering those packets and having errors and retransmitting packets and so forth. You'll probably still have problems if your competitors are using, again, parabolic dish antennas, if their towers are close enough to yours, if they're co-located on the same tower. They still have huge side lobes that will send noise to your area, so there'll be some interaction. Again, your backhaul links will improve, but they'll never really improve as much as they could if everybody was using this technology. So if your competition also switched over to using horn technology on their backhauls, you can start to see now how much cleaner everything is, how more precise the radiation angles really are. Knowing exactly where you're sending the signal and knowing exactly where you're receiving signals from makes your network much more stable, and really long-term, your ability to plan your next deployments, to plan your next backhauls, to plan your upgrades to increasing backhauls, adding more backhauls, really becomes possible when you use antenna technology that's stable, that's precise, and that's repeatable. And that's the key. So just to drive it a little bit further, let's look at the linear scale of a parabolic dish antenna. This is a 10-mile link, and you can see the main lobe. If we look back here, this is actually the intensity and how far those side lobes go. So it's really not that small, right? When we look at the polar plots, we see this huge main middle beam, and then we see these little side lobes at the bottom, and it's really difficult sometimes for people to really put it in perspective what that means, because the side lobes are usually, if you look at, again, the polar plots, of the side lobes are usually like in the neg, 14, neg 15, even neg 20 potentially, whatever it may be. But that still has, anywhere from 10 to 15 dB of gain, right? Maybe slightly more, slightly less. And the side lobes of these parabolic dishes are capable of going almost 2 kilometers away from the tower. Look at the horn antenna to the right. You can see that the directional pattern with no side lobes is much more cleaner, and there's less interference to be sent or receive. So again, it's very easy to have another competing tower 2 kilometers away from you, or even your own, like in this micro pop world where things are getting even smaller, even closer. It's very possible that your backhauls are causing issues because of their side lobes, even though we mainly focus on that main beam gain and main beam angle, right? The side lobes are something you seriously have to consider and do something about. If we move to point to multi-point, the same thing applies, right? So let's say here we replace a single 120-degree sector with 2 60-degree horns, right? So we can see that the noise area has reduced because now you've removed the side lobes from one traditional sector. It's still pretty busy, right? Your symmetrical horn antennas in that peach orange color there, they're going to start doing much better because now at least they're not fighting with each other because they have good beam patterns. They have really good noise isolation. They have really good beam performance. So the signals coming in from the CPEs are being handled better. You have slightly less noise to deal with, less errors. So things start improving, but they still have to deal with the side lobes and the noise that's coming out of the co-located sector antennas that are on there as well. So it's not until you remove all your traditional sectors and do nothing but symmetrical horn antennas that you really ever truly achieve the massive scalability, the high density, customer counts per tower, the really high sustainable high bandwidth packages that your customers are demanding, even being able to deliver the bandwidth that your customers are paying for, right? So really, horn antennas or antennas with no side lobes really make the biggest difference in the world for how your ISP runs, how reliable your service is, and really what your reputation looks like in this industry, which we know is really important. If we look at symmetrical, traditional patch array sectors, again, on a linear scale, we can see the size relationship of the main lobe versus the side lobe. Again, side lobes look kind of tiny, but when you actually measure them, you can see that they go pretty damn far, right? I mean, 500 meters is a long distance. Most people are doing micro pops within this distance, and they're using these same traditional sectors or these same patch array sectors in these micro pop or mini pop environments. And really, you start adding up all the side lobe interaction, the gain is really intense at these short distances. And there's a lot of interaction between, again, your coverage areas. Never mind the huge forward gain that you have coming out of this main lobe as well. In micro pops, really, lower gain horn antennas are the only way to go to really give you that scalability you need, the repeatability that you need, and the sustainability to continue growing out your micro pops. So there's more to noise rejection than just no side lobes, right? And precise radiation angles. Really, it's about gain as well, using the appropriate gain for your coverage area. So if we look at the pink and blue areas, we can see the area of reception in pink and the area of transmission, right, in blue. And this is based on TX power. TX power is adjustable, right? So you can grow and shrink your coverage area by adjusting TX power. But receive gain is fixed. It's the receive sensitivity of your radio on top of the fixed gain of your sector. So this is something that really can't be tuned down or adjusted in the radio like you normally do for your coverage area and your TX power. So when you have areas where the coverage isn't going out very far, why use really high gain traditional sectors? If you use appropriate gain horns or even appropriate down tilt, you can see as we reduce the gain of the horn or the reception, we start now reducing the noise level of competing APs out at a distance, or again, even other noise sources that may be coming in. So it really doesn't make sense to use these really high gain patch array sector antennas for the new world of smaller and smaller cell coverage from our towers. Again, using appropriate down tilt for higher gain horns, or using lower gain overall, depending on your density and how you have to build out your network. You really get that granularity with horns that you don't get with traditional sectors. So if we look at kind of, wrapping up the three main rules for noise rejection, again, it's really deploying antennas with no side lobes, right? So the smaller the side lobes, the more non-existent the side lobes are, the better your network is going to operate, right? It's really going to perform at its maximum capabilities when you reduce all these receptors of noise and things that interfere. So using RF elements horns is clearly the way to go to eliminate that issue. Installing antennas with appropriate beam angle, right? To only propagate and receive signal where it's needed or where it needs to come from, right? So, stop using OMNI antennas for sure, right? But really wide angle sector antennas to cover narrow areas of coverage area. Really, RF elements horn antenna technology is the key here. We have 7 different horn antennas that are on the market, everything from 30 degrees up to 90 degrees in 10-degree steps. So we give you that granularity. If you need to cover 30, if you need to cover 50, if you need to cover 70, 40, whatever it is, we have an antenna with that exact radiation pattern. So use it, and therefore you can again build your coverage based on where your customers are and not send signal where your customers are not, right? Because even though they're not there now, if you start sending noise where there are no customers, you might have customers there in the future, and therefore you want to leave that spectrum as virgin as possible for you to use later down the road, right? And again, this kind of leads into, again, using antennas with moderate gain, right? Don't overkill your network with TX power, right? Stay within your EIRP limits, and also, you don't always have to go to maximum EIRP that's allowed for TX power. If you're only covering a mile or two, you don't need the full, 36 dB EIRP, right? Tune it down a little bit, right? Save that spectrum, save that noise from going somewhere else. You could also be a good steward and pay it forward by helping, competing lists. We're all in this game together, right? And we all have this spectrum that we have to share together. So, if we start using it appropriately, people will see the benefits. They'll start using it appropriately, and it all kind of comes back together in the end and creates a much stronger industry as a whole, which is really important for us to think of the bigger picture, not just of ourselves, but where everything is going, where the challenges are that's coming in the future. And RF element symmetrical horn antennas really help us get to where we need to be, not only now, but in the future. So we have some new webinars coming out. So I'm just asking everybody to pay attention, follow us on Facebook, on social media. We have an Antenna Mythbusters webinar coming out here in the next couple of months. So keep an eye out for that. Again, follow us. We'll announce when it's available. We'll be announcing again specific webinars with ISP Supplies again, specifically on this one and others, right? So look out for our new webinars. We're really looking to push out some more information to really drive the point and really do what many manufacturers haven't done in a very long time, let's say, right? And it's to really show you how these things work, to really show you how this technology works, what the weak points are, and really how you can use this knowledge to your advantage. So keep an eye out for that. We should be coming out with some new stuff. We have a forum, rfelab.com. It's our community. We ask you to join it if you haven't. There's great information on there. It's a great place to go, potentially look for the issues that you may be having, and then reference a fix and how customers that have used our horn antennas have been able to overcome some of their problems and stuff like that. So rfelab.com, definitely check it out. It's a great place to start. And then YouTube, right? So we have great customer feedback, man. We have some great customer testimonials on our YouTube channel. So I ask you to go to YouTube/RF Elements and check it out. A lot of great information there. Some past webinars and other stuff there. But there's nothing better than just watching what other WISPs have done and what they really have to say about the product and how it's helped. It truly makes a difference. It really helps you make the connection, because I guarantee you, if you're having a problem, there's a video out there for somebody who's having the same problem, and you can see how this technology was employed and helped them out. So stay tuned. Go to our website, rfelements.com. Join our forum, rfdlab.com, and we're all over on social media. So again, our YouTube channel, Facebook, LinkedIn, G+, Twitter, you name it, we're there. We look forward to interacting and talking to each and every one of you. So if anybody has questions, you can always reach out to us via email or social media. And again, we're here for you. At this point, I think we're ready for Q&A. If we have any questions and answers, I'll turn it over to Violetta, and we'll take it from there.
All right, Tessa. So there is a question. Will there ever be horns for a 2.5 gigahertz?
It's a pretty strong probably not. We've been asked for 2.4 gigahertz, and it's been pretty strong that the size of the horn, the ratio of size to gain in these much lower frequencies like 2.4 or 2.5 probably won't be as accepted as they've been. The noise isolation will be there, sure, but we think that for today's networks, it's probably not something that will happen. I think the 3 gig spectrum is probably a better floor for us as far as how far down we'd go in frequency. But yeah, 2.5 is not really on the roadmap at the moment. Sorry.
Okay, one more question, and we have another one. Any methods, tools you guys recommend for calculating mechanical down tilt?
Yeah, absolutely. Just go to our website. So we have a really cool link calculator on our website. It does both point to point and point to multi-point. If you go there, there's a couple of how to use videos on there you should probably watch before you try messing around with it, but it's pretty simple. I mean, you basically drop your pin where your AP is, you drop your second pin where your either point-to-point or point-to-multi-point customer maybe, and then we have sliders, right? So you can adjust. You can first off, you can pick the antenna that you want, whether it's a 30, 40, 50, 90, even our ultra horn and ultra dish, right? So you can pick the antenna type that you're trying to use. You then put in the TX power of the transmitting radios. You can also adjust the MCS rate, right? So you can say, if you want it for full 256 QAM, maybe you're happy with 64 QAM. Again, it's kind of important to know your radio technology. Like, let's say, for instance, you're using a Prism radio from Ubiquiti. It does 256 QAM, right? So that's MCS 9. If you were to use, let's say, a Cambium EPMP 2000 or something like that, or even EPMP 1000, the maximum is 64 QAM at the moment, which is MCS 7. So it's really important to know that, because if you have MCS 9 as you're selected in a radio that's not capable of going there, it's going to show you that the distance you can go is much shorter than you would expect. So again, there's a down tilt calculator. Once you get all your parameters in, then you could start adjusting down tilt, increasing 1 degree at a time, and you can watch your signal start to drop off until you get to a signal level that you're happy with, and then what's the maximum down tilt you can use. So yeah, rfelements.com/link calculator. You can find it on our website.
All right, any more questions? Well, okay, so we've come to the end. We are recording this live, and it will be posted on ISP Supplies YouTube channel. Additionally, I'll have the live recording sent to you through email. If you have any further questions, feel free to contact Tassos, right, at RF Elements, or our sales team at ISP Supplies, and the number would be 655-947-7776, or you can email us at sales@ispsupplies.com. All right, Tasso, thank you so much for presenting, and I appreciate everybody's patience and everyone that attended. Thank you so much.
Thank you. Bye.
Bye.